Okay, research methods class. This is sort of a mid-semester review, and then the majority beginning of this review will be concepts and visuals that I've created to sort of help get at the foundational concepts of research methods. And I want to re-emphasize that when we're talking about research methods, all of these things are tools to try to analyze whatever data you have, whatever question you have, and you may start at different with different parts of a whole research method. So you may start with a question, you may start with data and develop a question. And so all of these are sort of tools, and it's a skill to sort of understand what tools you might have and what sort of the steps are to developing a whole study proposal and actually implementing that study. So I want to emphasize that when we're doing research methods, we're making assumptions and about all of these tools, and there are strengths and weaknesses to all of these tools, so there's no one method that's the best. Everything is contextual, so it depends on your question, it depends on your data, but you need to sort of, if this is what you have and these are the tools, you need to sort of match what you have with the tools that are best to answer your question in the best way. So I just want to emphasize that because I know sometimes the quiz language can seem like it can be confusing, but a lot of it is because a lot of these questions are about the assumptions that we make. And so I'll be going over some of these concepts in the beginning, and then I'll be going over and going back to sort of this chart, which is you can think about as a roadmap for how we've gone through this course. We started with, okay, more abstract ideas and how we develop those into questions and how we incorporate theory. Sometimes you may be starting with a specific theory that you want to test, that you think is really interesting, but maybe there are no empirical analysis on that specific theory. And so these are sort of the foundations and the conceptualization, operationalization, population and sampling. So if we think about population and sampling, conceptualization and operationalization, basically everything in this map is going to be specific to the type of research method and data you have. So this all changes based off of like how you want to go about your study, and there's so many different ways you can, but there are also limits. So if you have qualitative analysis, it's going to be very difficult for you to do a regression, right? You're limited in the types of analysis that you can do, but you can also do a wide range of qualitative analysis like focus groups and all these different things. So research methods is sort of unique in that there's like no specific right answer for exactly what the path to developing a research proposal is, but instead there are a lot of right answers, and you sort of just need to justify your choices based off of your questions, your data, and what's tangible, what you tangibly have. So getting into the basics of this, and this is why I'm reviewing the basics again with you all, because these basic conceptions of operationalization, measurement are like really important for not only if you want to develop your own studies, but for you to be able to critique literature that might be relevant if you're not interested in going into research or academia, if you're instead interested in being a practitioner. It's really important for you to get these foundational concepts that we covered in the first 2 weeks of conceptualization, sampling, theory, validity, reliability, because once you have that vocabulary and those tools, you can look at the research and assess whether or not it's actually fits with what your literature review is based on. So let's say that you are a police officer and you want to understand the best way to engage with youth. This is an example I've used before. So in order for you to do that, you might look into specific experiments that have done this, or specific surveys, or any of these other things. And in order for you to develop like a policy recommendation to your department, or to outline a policy memo to your department or whatnot, to synthesize the literature, it's important for you to think about conceptualization, operationalization, sampling, and sort of the larger questions and how they relate to your specific interests. And these foundational concepts, the conceptualization, operationalization, population sampling, validity, reliability, will help you assess whether it applies to your specific context, and also what you can take away from these research studies that are helpful, and what you can say that's not helpful within my context, and like I'm going to ignore that study because of this, this, and this. And so this is how you can be better informed consumers of research, is by having these foundational concepts down packed. So even if you're not going to go into research or academia, it's really important to have the language to be able to critique all of these empirical papers and qualitative methods, books as well. And even like qualitative methods is also when you read news articles and reporting, that type of stuff is also qualitative methods. So if you get these foundational concepts down, you'll be a better consumer of research in general for your own purpose and needs. Because every empirical paper is not the be-all, end-all of truth. There are aspects of truth that are in it, and some of that truth applies more so in other contexts, and some of that truth is specific to certain populations and whatnot. So it's important for you to get at the truth that you want to get these foundational concepts down. So I think I made my soapbox apparent on how important this is, but I really do want you all to take away what's most practical for you. So, going quickly over, there's measurement, which is, we can think of there's measurement in each specific variable that's in our data. So measurement can be talking about so many different variables within our data at one time. And so for each variable that we measure, there's reliability and validity. And we'll get into it later, but reliability and validity also show up when we're making causal arguments, and when we can use them to also describe different types of research methods. So measurement is in the conceptualization and operationalization portion. It's like how the definitions that are abstract get measured into tangible, quantitative, ordinal, categorical data. And then also has a little bit to do with population and sampling too, because that's where we're taking our measurement from. And then reliability and validity also show up in the type of research method that we're doing. So different research methods have better reliability or validity, and all these generalizations are within limits and context. So we'll get more into this, but I just want to emphasize that reliability and validity show up in measurement, which is with individual variables, and then it also shows up in the type of research method that we're using for the entire study. Not just the data, not just the variables we're measuring, but also in how we're conducting our research, if it's a survey, if we're constructing it, or if we're observing in a qualitative setting and more of a participant observation. all those different methods have varying reliability and validity. So when we're talking in a more smaller level of just the variables within our data, age, race, gender, numbers of times arrested, sentence length, all of these things are measured and captured, but like everything, there's error. So the way that we describe the quality of our measurements is reliability and validity. And so we want to be precise. And I know that people were sort of confused towards whether mutually exclusive and exhaustive were measurements of quality, and they're not. They're sort of like the standard for variables, is that they should be mutually exclusive and exhaustive. But how we can categorize and describe variables is instead reliability and validity. So each variable has a higher, lower level of these qualities. So when I gave sort of the car example in the initial lecture on this. So when something is reliable but not valid, it is going to look, an example of this is going to be a car that's going 65 miles per hour, but the cop that has the speedometer is off by 10 miles, and it's saying that it's going 75 miles per hour every time that car goes by. And so it's reliable, it's consistently saying the same thing when it sees an outcome, that is outcome 65, it's consistently giving 75. So with the same input, it's giving the same output. They're always the same. But there's a gap between the two, so it's not valid. It's not saying what the actual truth of the miles per hour the car is going. So therefore, it's reliable. Every time you put the input in, it gives you the same output, but it's not valid. So think of reliability as, if I were to repeat this over and over again with the same input, would it give me the same output? And this example is sort of reflective of the issues with reliability. So when we're talking about machines that are programmed to give you the same output for an input, they're very reliable, they're consistent. But if we were to use people, they may not be as reliable because some people may observe inaccurately, and this is like inaccurate observation, which is a question that came up in the discussion post. And so if you have something that's reliable but not valid, then that's inaccurate observation. It's consistent, it's reliable, but it's inaccurate to what actually is the true measurement. And then there's validity. So this is valid but not reliable, because this is like if the speedometer, every time a car was going 65, every time it got that input, the speedometer gave you a wide range of outputs. So maybe it said 75, 60, 67, and it was sort of all over the map. It's not consistent. It's not in the same space. But if you averaged all of these together, it would be accurate. So issues with being valid but not reliable is that then you need like multiple observations to get at the truth, right? And this is an example of neither reliable or valid. So it's definitely, if you average this, it would be it would be a higher miles per hour than at the center here. This is not if you average this, would be at the center and the true accurate target of your measurement. Instead, it's going to produce bias by being above the actual measurement that you'd like. And then finally, this is something that's both reliable and valid. It gets at what the actual measurement is, 65 miles per hour, and it does it consistently. Every time a car goes 65 miles per hour past the speedometer, it says 65 miles per hour. So it has no error in the measurement because it's reliable and valid. And so a way to think about each variable that you collect is to always map the distribution and frequency of the variables you're getting. So we can think of this if it were a continuous variable, in which there are measures all along this spectrum. And so for each time it says 0, this is the frequency of the number of observations you have for 0. Right here. And each time it says 6, this right here is the frequency of the number of observations you have that are 6. And so you see here that when we're talking about a specific variable, we can talk about the mode, mean, median. So for example, I told you guys for your grades that the mode, mean, and median was B. That's the average, the mean, and the mode, and the median. So if that's true, and the mode, median, and mean are all the same, then that means that we're in a normal curve. So some students, which are my sample population, fall outside and are not the mode, mean, and median. They're not a B. Some students have a C over here. Some students have an A. But the grade that is most frequently seen, the average, and in the middle of the distribution, so this would be A, this would be B, and this would be C, is B. So that doesn't mean that all my observations are B. That just means that my observations are centered at B. And we can see that that doesn't always happen. We don't always have this nice bell curve. I was thankful that for this class we have this nice bell curve, because that shows that there's some variability in the class, but no one's doing super, super well as to be an outlier. No one's doing super, super bad as to just be like really struggling in the class. So if this were to look differently, then maybe it would be that most people got a D, right? And so this is what this would look like if we were talking about the distribution of grades in a class. So if most people got a D, then this means that the mean is not going to be an accurate picture of sort of what the most frequent grade is. The most frequent grade is always going to be the mode. The mode is the amount, it's like the peak of the distribution. So it's the output that we see the most of, that is the most frequent distribution. So if we went to every person in the class and asked them what they got, we would hear this the most. But if someone were to ask me to guess what the average was, that would look different than the mode. And so this shows a distribution that's negatively skewed. So an example of a negatively skewed distribution like this could be let's see, like stocks and income and stocks, right? So not a lot of us have that. Maybe we have a little bit of it, but the people who do have it may have a lot of it. And so it's important to recognize when you're looking at the specific variables that you're looking at, how this is distributed, because this means that there are outliers that have no stock, and then but most people have some stock, right? And so it's really important to visualize your variables so you know how they're distributed, because this allows you to get a better understanding of what it looks like, especially if you have done probability sampling. You can also sort of make generalizations about the larger population parameter that you're interested in. So let's say you did a national sample of people who have parents who are incarcerated, right? So if you counted the number of people, then you could make generalizations about the larger population by just that yes/no variable, right? And we'll talk about the best way, because for different types of variables, like this is really great for continuous variables where there's a number, like say age. Like you could easily think of this as an age crime curve of like when a person first started did their first crime. Like it's going to be a younger generation, and then it's going to wean off as it gets older. And so age, money, like things that are on a continuous spectrum are really nice to visualize with the mean, median, and mode, because you sort of get a sense of the entire distribution. And if there are outliers, which are not bad, that means it says something, that there are some people or institutions in the population that you're looking at that have like a very large amount of something or a very minimal amount of something. And so it's important to use these to understand how that distribution works and to understand your variables better. And so mutually exclusive and exhaustive are characteristics of variables that we need. So every variable needs to have these things. So when we're talking about mutually exclusive, I took some examples that you all put on the discussion board that I thought were pretty good. So a variable is mutually exclusive when it cannot occur at the same time. So for example, you can't jog forward and backward at the same time. A mutually exclusive variable is something that cannot happen at the same time. And I adjusted this example a little bit. So a criminal justice example would be one person not being able to be arrested for the same crime and at the same time, but in different places. So you can't be in two places at once. You can be arrested for multiple crimes, right, in different times in different places, but you can't be arrested for multiple crimes at the same time in different places, because you can't be in two places at once, right? Another example is a coin toss, because the coin cannot land on both tails and heads simultaneously. Yes, and a coin toss is really helpful for understanding binary variables, yes/no variables, present, not present. And so think about that metaphor when you are analyzing those types of variables. So exhaustive is when you are making sure that the variable, the attributes that you're providing for your variable, ensure the full range of possibilities. So you want to make sure that you have this full range of possibilities, or you might be not counting a possibility and that could cause bias. And this is all at the measurement level. This is all at the individual variable level. So an example is grouping participants in a survey by age category. It is mutually exclusive because no one could appear in more than one category. It is also exhaustive because the age groups cover the entire range of the population ages, right? So we know that there are some outliers in age. There are people who live to 105, but if we provide a numeric category for them, they can fall within that range, right? Variables need to be exhaustive so that all possible outcomes can be determined. Yes. They all need to be exclusive so that variables are not double counted. Also, yes. An example of an exhaustive variable would be gender. Gender could include not just male or female, but it could also include male transgender or female transgender or any other gender. Yes. Non-binary, too. Rolling a six-sided die, the events 1, 2, 3, 4, and 5 and 6, each consisting of a single outcome, are collectively exhaustive because they encompass the entire range of possible outcomes. That's completely true. So I think these examples are all really good, and I think the gender one is especially interesting because if oftentimes in surveys and whatnot, we only put male, female, so we could be creating barriers or creating systemic bias if we're not including other genders as well, the exhaustive spectrum of gender. So we're still at sort of the variable data level of analysis, right? And so there are qualitative variables and then there are quantitative variables. So we've sort of been more talking about quantitative variables when we're talking about mean, mode, median. And so quantitative variables, you can think of them as numbers on a spectrum, and there is a hierarchy to them. And then qualitative variables are more categorical. We create a nominal variables. We're sort of creating and constructing attributes. Ordinal are somewhat numeric in that they have a spectrum by which they are, but we don't necessarily, the intervals between them are not necessarily equal. So examples of nominal variables are gender, race, city or residence, social security number, marital status. So these are merely labels and characteristics. They have no inherent value to them. They're sort of just categories, and they fit mutually exclusive and exhaustive requirements. And then the ordinal fits those requirements, but logically ranks these categories in an order. So a police hierarchy, there's the chief and lieutenants and captains, and they all are composed within a hierarchy. Occupational status, there are occupational statuses. We can rank by prestige, or we can rank by the amount they get paid. There's crime seriousness and fear of crime. And I think, so interval is when the actual distance that separates the attributes is equal. So temperature, frequency, age, crime rate. And crime rate is something that's based off of a true 0 point. And examples are age, dollar value, prior arrest, blood, alcohol content, and length of incarceration. And we'll talk about ratios and rates because they can be a little bit confusing. But you're getting a lot of information when you have a ratio. It's oftentimes you're getting multiple points of information. And there are implications for each level of measurement. So there's assumptions we have of each of these levels of measurement. So, and we can use different statistical techniques for different types of measurement. So regression analysis is really easy to do with ratio and interval variables because it sort of meets the standards of that, whereas ordinal and nominal, we need to use different types of statistical analysis. And so we can think of these as different levels. So ratio is the highest level, and then nominal is the lowest level. And these are characteristics that they all meet. And so ratio meets all of these characteristics at the same time. That's why it's in each of these categories, whereas interval meets all of these characteristics except having a true zero, and ordinal meets all these characteristics except having a true zero in equal interval. And so sometimes we can convert these different things into different levels. So we might have a percentage of race, which is a variable that distinguishes counties, or we might have a percentage of immigrants, right? So these are nominal variables that we're constructing into rates and ratios to categorize different spatial units. And we can construct those, but it's hard. We can construct those into like rates and indexes, but we can't reduce. We can't really convert a lower level measure into a higher level measure unless we have like multiple forms of measurement within that. And I'll get into that in a sec when we talk about rates and ratios. So back to this diagram of the different types of data that we have. And I guess frequency makes sense if you're talking within a Likert scale. So if you're saying that how frequently you exercise and you're filling out a survey and you're saying very frequently, somewhat frequently, less frequently, never, right? We don't know that those intervals are the same between them. And so we have to think about what the best measure of central tendency to analyze within these specific types of data. So for ratios, we can usually use the mean, mode, and the median because if we take those outcomes and put them on x-axis, we can see the number of people who do that, and we can draw a line because there is a true 0 point, and we can sort of present a curve. So we can use the mode, mean, and median to analyze ratios and understand how they're distributed within our population. Ordinal variables, we can only use the mode and the median. The mean doesn't mean as much in this situation, although we could use it. It's sort of not as helpful. And when we're thinking about nominal, we can only use the mode. So we can only use the thing that occurs most frequently. The mean and the median will give us some information, but it's not going to be super helpful because what does it mean to be an average of, like, if we're putting numerical if these are categorical variables, you can't really say what a number in between them is, right? Instead, it's like which categorical variable occurs the most frequently in your specific population. Or you can turn these different nominal variables into rates of your specific data, right? So the percentage of people who are public policy majors, or the percentage of people who are criminal justice majors. And a rule of thumb from your book is you cannot convert a lower level measure to a higher level one. So we can convert higher level measures into lower level, but we lose some information. And sometimes that's helpful to lose some information. But I think it's good to sort of see this in a visual format, because you can see sort of like the stairs of no and yes, but we lose some information. Forward this PowerPoint. Okay, sorry about that. So when might we want to lose some information in our variables? So ordinal to nominal. If we're testing the ordinal nature against more quantitative metrics. So if oftentimes risk assessments will have a ranking that it develops. So if we're trying to test that, we might reduce the ordinal into nominal variables. If we want to create ranges or typology, for example, age ranges, we might convert an interval into an ordinal. So we might create categories like 0 to 10, 10 to 20, that meet sort of our analysis's needs. So if we're thinking about generations, it might be better to categorize people into different generations than just taking their unit of age. And we might want to reduce ratios into ordinals if we want to create ranges or typologies again. So if instead of how much people make per year, we instead want to categorize people into lower class, middle class, and upper class for analysis, that might also be helpful. And so getting into rates versus ratios. So in math, rates and ratios are very much different, but in social sciences, they're a little bit, they bleed more into each other. So rates are types of ratios in which the units of analysis are different, and time is usually incorporated into it as well. So crime rates are for a designated year, the amount of crime that occurs in a space per population. So we do the per population, so it's comparable across units. So it's a rate that involves time, space, and the space is determined by a population within a geographic area. So interest rates are the same unit. We're talking about money, but it's a percentage of money that gets added each year over time. And creating rates is really helpful for comparison, especially in social sciences and criminal justice, because it can help us categorize geographic spaces. So we can understand under-policing or over-policing by determining a rate of policing per population across different areas. We can understand expenditures of government, so we can calculate the rate of spending on police per different areas and populations over years. And we can also develop demographic rates, right? So the percentage population of people of color in a specific area or immigrants, and that can help us sort of analyze how these all relate to each other and what other things might inform these specific rates. So rates are really helpful in social science, and if you're analyzing especially national data, you'll often be using rates. And especially too if you're analyzing like higher order variables, so communities, institutions, not at the individual level, if you're not interested in individual behavior, but instead how systems work, rates are going to be very helpful as well. But there's also, like if you're looking at more individual analysis, that also can develop causal claims and say things about things, but your unit of analysis is smaller and you're not really dealing with rates as much unless you're dealing with them. Most rates are not at the individual level. And so composite measures are often also used in social sciences because they allow us to take abstract ideas and make them into more concrete, tangible metrics. So 2 examples I'm going to go over are collective efficacy, which is used in social disorganization theory, and risk assessment, which is like very big in criminal justice as we've moved more to data-driven analysis and like trying to reduce risk in general, where like risk is a big concept that people are really acclimating towards and is sort of being perpetuated in the criminal justice sphere. So this I took directly from an empirical paper on social disorganization. And so remember that social disorganization, collective efficacy is sort of a measure of social disorganization. So if there's high collective efficacy, there's going to be low social disorganization, or that's how the theory goes, right? So empirical studies try to test social disorganization, and they've come up with collective efficacy to try to conceptualize and operationalize the definition of social disorganization. So directly from this empirical paper, they say to measure the social control aspects of collective efficacy, residents were asked in a survey about the likelihood that their neighbors could be counted on to take action if. And here are the different survey questions. If children were skipping school and hanging out on a street corner, if they were spray painting graffiti on a local building, if they were showing disrespect to an adult, if a fight broke out in front of their house, if the fire station closest to home was threatened with budget cuts. So depending on these answers, there's an index score that gets developed. So there's likely yes, no binary outcomes, or maybe they put it on a Likert scale of very likely, extremely unlikely, and there were spaces in between. So the scores get added up, and the more that the higher the scores, the higher the collective efficacy, and the lower the scores, the lower the collective efficacy. So this allows that sort of abstract concept of collective efficacy to show up in different instances and to be measured. And so you can collect data on everyone in a specific neighborhood and what they think and come up with the aggregate of it for a specific community. So this shows how like 5 questions that are seemingly individual can be developed into larger composites to categorize different neighborhoods. So the public safety assessment, which is used in New Jersey's pretrial court hearings, to determine, like prior to being convicted, whether or not you're going to be put in jail, is based off of a public safety assessment score. So you see that there are different monitoring levels. So the highest monitoring level is detention. The lowest is you get released and you just need to come back to your court date. And there's various level of reporting and monitoring in between. So you could need to report to pretrial services weekly, monthly, via phone, or via in person. And so there's these scores that develop for these 3 categories that help judges determine the level here. So there's a failure to appear score that is constructed based off of these data, so whether or not there's a pending charge, prior conviction, and prior failure to appear. There's a new criminal activity score, which is based off of all of these factors, and then there's a new violent criminal flag based off of these factors. So these are the variables that create the larger composite score, and you see these 2 are 1 to 6, and this is a binary variable or a flag. So the Arnold Foundation, which developed this, created these composite scores, and there are other risk assessment tools that use different variables to develop these scores. So if you were to analyze whether or not these things work, you would be looking at where they're getting their data from, and also whether or not you think these particular scores are operationalized in the right way for these particular categories. So in learning about operationalization and validity, we can sort of critique tools that are being widely used as indexes to determine whether or not people should be detained in jail. And there's a lot of research and money going into trying to determine the best way to predict these things. So those were 2 examples of indexes that are used in the criminal justice system. So it's taking variables that are smaller and making composite scores into a larger, it's taking things that are more tangible and putting them into definitions that take more abstract concepts and make them quantifiable, able to be counted. So when we're developing this data, like we talked about, we're usually sampling. There's not many instances in which we get an entire population. There are some governments, like some European governments like Sweden, like the second you're born, they're always collecting data on you, and they have like a wide range of data on their citizens. But the US is a bit more private when we're talking about data, and data collection is sort of privatized. It's not done through the government as much. We have sort of more limits on that. Some other instances in which you may have full data are universities have a lot of data on their students, employers have a lot of data on their employees. Maybe you guys can think of other instances in which there would be full data that is collected. But the data that is collected by universities about their students is usually just demographic and descriptive. It's not so much behavioral, where we can analyze how individuals behave in specific instances. So it's very specific to the place and context. And usually universities collect some data on behavior, like time to completion of diploma, but that's more for their own internal analysis and metrics of their own. But when we're doing more social science research, we're trying to collect our own data to see more of the relationships between variables and not just look at the demographic descriptive statistics. So that's more of the academic lens towards it. So we try to sample population and make generalizations about that larger population. If you're trying to develop more metrics for like program evaluation, if you're working in a like rehab clinic or whatnot, you might have a lot of data on the participants that are there, and you could do things with it, but there is a filtering process of how those people end up in your specific program that you need to be aware of too. So you can't make generalizations about people who struggle with alcohol and drugs because the data you're collecting is within your world bubble of the people who come to your specific program, right? And so this gets into the different types of sampling. So if you have a program where people come to you, that's non-probability sampling, right? There's a system in a way in which they get referred to your specific clinic. A different way that could work, and a way where it would be probability sampling, if people got services at random. Like, so if everyone who did have issues with alcohol or drugs randomly got selected to be in a program or not, that would be a way in which it would be probability sampling. So probability, remember, is that there is a random chance for each person within a population to be sampled. And there are different ways that this shows up. So I just want to reemphasize, each person has an equal probability of being sampled. But it doesn't mean that the sample that you get is going to be representative of the larger population. So especially if you have people who fit more minority categories and are not a majority within your larger population, they may not be as visible in your sample because there are less of that specific population. So that's why people use disproportionate sampling. They stratify based off of race or based off of vulnerable populations, and they oversample the people who represent a smaller majority of the larger population. That way they can make generalizations about them, because if they do simple random sampling, it's not guaranteed that that sample is going to be representative of the larger population. And that's going to depend on the interests of your study, right? You may, usually in social sciences, we all usually try to measure race and class and poverty because they're very important for things, but maybe you're looking at things more from an individual behavioral level and you're not measuring those things. It really depends on your questions and trying to reduce the bias, and looking at the literature of what other studies have included in their variables with similar questions. So that's something too that's sort of like a tip that you can do, is if you have a specific question, you can always look at if someone else had that question and how they went about answering that question, what types of methods they used, and you can like replicate that study in your own space with your own sample. And there's really a lot of room to repeat or build upon prior people's studies. You just need to cite them. And so I just wanted to give you guys sort of like a diagram of how these are all connected. You see here that multi-stage clustering with stratified is connected to both of these. It's sort of a mix of probability sampling, and these are non-probability sampling. So sort of to recognize that in probability sampling, because we have some statistical components of randomization probability, we can assume the error. We can calculate the error of our sample to the broader population, and in our statistical analysis we can calculate the outputs that we get, the regressions that we get, what the error is there too. When we're analyzing non-probability samples, we can't do that. We can't make generalizations about our error. Instead, we don't really know. We're sort of in the dark as to how error might be showing up in our sample. We can address it and we can talk about it, but we can't say for sure systematically and measure and quantify what that looks like. And there are benefits and weaknesses to both of those types of approaches. And like we talked about, non-probability sampling is often useful when we're looking at a population and really wanting to understand their perspective, or we have like a very specific question that hasn't been looked at before, and we don't necessarily want to make generalizations. We want to do more exploratory and descriptive analysis. But when we want to do explanatory or causal analysis, we need probability sampling. Okay, so I just wanted to show this chart because some people had a bit of issue trying to understand the relationship between standard error and sample size. So like we talked about, standard error only exists in the probability sampling realm. We can't get standard error for any of the non-probability sampling that we've developed. And so as standard error goes down, it's because your sample size is getting larger. And we saw that when I showed you the demonstration on how if you repeated your samples with larger and larger sample sizes, you get closer and closer to the parameter estimate. So you're getting closer and closer to the truth of what the actual parameter is. And so this is very much like rooted in statistical concepts and analysis and theory. That's like not necessary for you to know, but you do need to know that as sample size increases, your standard error gets smaller. And this is all within probability sampling. Okay, so just to go over the types of sampling very quickly, simple random sampling is like the simplest way to get non-biased sampling. It doesn't necessarily mean that you're going to get representative samples, so you're not necessarily going to be able to analyze differences in your population characteristics to others. So like I can't necessarily, because I only have one blue person, I can't make generalizations about teal. I guess this is teal, this is blue. I can't make generalizations about this teal individual, but I can say things about the entire population. Systematic sampling is often used more frequently than simple random sampling, but it's just a form of randomization that's done based off of the researcher. So the researcher counts every 3 individuals in this instance to collect data from. But there's one danger in that if these people are flowing into your research in a specific way, like in a specific time or seasonal way, then you're gonna get errors within that. So if there's a pattern behind how people are flowing into your study and you're only taking every 3, then you might be replicating or taking only a certain aspect of that pattern. Then there's stratified sampling, where you, prior to collecting the data, you sort of divide people into categories, and then you take the same amount that's proportional to the larger population. So if there's, if the general population in the US is like 60% white, which I think it is, then you take your sample will be comprised of 60% white. So you're going to make sure that your sample is representative. So in stratified samples, you are ensuring that your sample is representative and is also randomly selected, which is very common in social science research. And then disproportionate stratified sampling is when you're very concerned with a specific population, so you might overrepresent the teal people because even though they're smaller, you want to make larger generalizations about them. And then cluster sampling is sampling of groups of elements followed by the selection of elements within each of the selected clusters. So this often happens, like if you're doing a national sample, you'll take a certain amount of people within zip code. So it's like this list and select type thing where you're listing. Maybe you can't get the full list of everyone in the US population, but you can get the full list of zip codes. And so you select from zip codes, and then you select within those blocks of zip codes and whatnot. So you have a smaller list that you're working with, and you select, and then you develop a smaller list, and you select. So it's sort of this cycle of doing that. And it's very efficient because it's really hard to develop a full list of the larger population, but it can be less accurate. And then we've talked about this before, but I thought the visual was nice. So convenience sample is when if you go to a particular event and you just try to recruit people who are near you for your study. A voluntary response sample would be like if you put your survey into the internet and see who went to go take it. A purposive sample is if I emailed, like say I was wanting to get correctional officers' opinions on something, if I emailed different correctional associations and said, please, I'd like 5 people from your organization to respond, could you please make sure that happens? And then there's snowball samples. So if you have informants in a particular different demographics or areas, and they refer you to people who would qualify for your study and fit the population that you're trying to sample from. I thought this was a helpful table for you all. It gets at the definitions, the advantages, and the disadvantages. And I'll post these slides so you guys can review this more on your own. And so like I was talking about before, validity and reliability are key to how we talk about studies, how we talk about measurement. So there's how we talk about measurement, and then there's how we talk about studies. And I went over in measurement that reliability is being able to get consistent results, and then validity is being able to get the accurate results, right? And so you can see these for measurement, but you could also see these within research. And so not all research studies are going to have perfect validity and reliability. Some may be skewed more to having higher validity and lower reliability. And so that can be a criticism you have of the study when you look at it. So when you're looking at studies, reading empirical papers, or developing your own studies, this is how you characterize the research methods. Okay. And I developed this chart for you all to understand how validity, which is a broader concept than reliability and has very different levels to it, can be seen in both measurement and in more causal and research methods characteristics as well. And so construct and external validity deal with generalizability, whether or not you can take your study and say it applies to other spaces or contexts. And then statistical conclusion and internal validity have to do with bias. And when we're talking about validity within not just the measurement sphere, but also within the research method sphere, we're talking about how logical relationships between variables is known. And so So an example I have for you is if a researcher is interested in attitudes towards trying juvenile adults and plans to assess support for this hypothesis by asking whether or not subjects say they would travel to countries that allow juveniles to stand trial as an adult, people would say that that lacks face validity, that you're not actually getting at the measurement that you're trying to get. That question is a little bit off tangent to what the real question that you're asking is, which is what like support for trying juveniles as adult. If you instead up front asked in a survey the general population whether or not they support trying juveniles in adults in a variety of specific instances, you gave them like different types of trials in which that may be an option, then that better gets at the question at hand and has more face validity. So face validity really just has to do with whether or not the mental images of your question are getting that respondents get are getting at the question that you actually have in the measure that you're actually trying to measure. Criterion-related validity is comparing a measure with some external criteria, and this happens more in like psychology or like the hard social sciences. There are often like external criteria that people can rely on, and since criminal justice is intersecting with psychology, you can use those types of measures as well. Then there's construct validity, which exists in both the causal and measurement worlds. And so in the causal world, it's more about whether or not the relationships between variables that you're constructing make sense. And there's so if you're wanting to make sure that not only the measurement of those specific variables has face validity, has criterion validity, has constant validity, but that the way that you're setting up those specific variables makes sense. So the time ordering needs to make sense as well, especially if you're talking within a causal link. If you're talking just association, then you're not going to have that many challenges. And so other threats to validity are history. So oftentimes we're working with data that is just a snapshot of a particular space, so we don't know if there was some historical incident that may have created biases in our data. And then other ones are just influences of being tested. The influence of, like, if you're doing more of an experiment where people are being tested, there's definitely biases that occur when someone is being told what to do, someone in a lab coat, right? So this shows that there are strengths and weaknesses. Like, often experimental methods are shown as like the be-all, end-all of being causal, but they also have weaknesses in that they're like highly constructed in nature and are sort of contrived. And then I just want to go over statistical conclusion validity. And external validity. So external validity is whether the results from the experiments in one setting will be obtained in other settings. It has to do with generalizability as well. So if you're measuring your constructs in a way that's not accurate to how other people measure them in other spaces, then you're not going to have generalizability as well. And so statistical conclusion validity has to do with like the statistical theory behind our methods, and oftentimes experimental methods depend highly on statistical conclusion validity. And so this depends on like how you're sampling, and if you have a small number of cases, then you're going to have low statistical conclusion validity, whereas if you have a higher amount, you're going to have a high amount of statistical conclusion validity. Okay, and I just want to get at experimental mortality versus panel attrition. This was a difficult question on the first quiz, and both involve someone falling off in a study, but they're specific to the type of study. So experimental mortality has to deal with people falling off of an experiment, and sometimes this literally happens with people like passing away. And panel attrition is more when people who are in a panel study, which is a study that occurs like every 6 months, you get asked questions as sort of follow-up. It's following like a group at multiple stages in their life across time, and sometimes they fall off and you don't reach them anymore, right? And so that's panel attrition. And so panel attrition is what Professor Hardy, which was one of the questions, was experiencing. So over the course of 10 years, he was doing this study, which means that it was a panel study, not an experiment where there's a pre-post. And a lot of people moved away, so this is panel attrition. And I want to make a distinction when we're talking about units of analysis versus findings. So oftentimes our units of analysis are smaller, like how we're analyzing the data is smaller, and our findings, especially if we're working within probability sampling, can be about broader, higher order variables. So, for example, the question that stumped some people was a survey distributed on a college campus discovered that males support the death penalty in greater numbers than do females. And the units of analysis in this case are individuals, but the findings are based off of groups. So you are analyzing individuals, but your findings are based off of male versus female. But the space in which you're capturing the data is in individuals. And then this one is an example I provided in a previous lecture. In this article, I introduced the concept of system avoidance, whereby individuals who have had contact with the criminal justice system avoid surveilling institutions that keep formal records. So she's looking at specific individuals, and that's her unit of analysis. But this broader concept that she has is system avoidance, which is not individuals, it's a larger institutional framework. And I just wanted to emphasize that multivariate analysis, which is analysis of two or more variables in relation to each other. Someone had a question of whether or not, like, if you analyzed each variable on its own and then talked about it in a like compared the results versus analyzing multiple variables at the same time. And so I just want to emphasize, when you're doing multivariate analysis, you're often doing regression analysis, which allows you to not only understand the relationship between X and Y, but to also predict it, and to, with your control and covariates that you're controlling, to also understand how they're related to X and Y. So you can't get that level of relationship and analysis and just doing individual analysis of variables. It's not as dynamic. So most social science research, like your bread and butter of statistics is going to be regression analysis. And then I just want to emphasize that quasi-experimental designs, which are super complex, and in all honesty, like a lot of people, like PhD students, don't do them very frequently. They're sort of hard to understand, but you can do them. You just need to know that there's no sense of equivalence in the study design, so you can't ensure that there's randomization in the same way. So what you do is you sometimes match populations based off of propensity scores, or you do time series designs to try to isolate the variables in time in that specific instance. So it's developing an experiment, but instead of doing the randomization, you're instead applying statistical analysis to it. So when there's non-equivalent group designs, what happens is you match them based off of different variables or whatnot to make sure that the two groups are equivalent. But yeah, these get pretty complicated. Then there's also cohort designs, which is specific to non-equivalent control group designs. And this is when subjects who enter or leave an institution at the same time. So a class of police officers who graduated from a training academy at the same time. In being a cohort, there's a level of similarity and equivalence. And so when you're comparing those things, they're more equivalent. So you didn't randomize those things, but the group or population sample that you're looking at has a level of similarity that can be there in lieu of randomization. And then longitudinal studies provide a way of developing causal analysis as well. And so because you can see the causal ordering of things, you can identify whether or not the intervention changed things by developing a trend line. And if when the intervention happened, that trend line divulges or changes, you can measure that difference. This is still about regression analysis. And so explained variation is the difference between the total variation and the unexplained variation, and dividing that explained variation by the total variation produces a measure of the proportionate reduction of error, and it corresponds to a similar quantity in computation of lambda. So basically, this is all to say that these are measures of your model. So your model is the explained variation, and that percentage is how much your model is explaining within your model. And the unexplained variation is how much your model is explaining things on known values of X. So these are all just sort of characteristics of your model when you're doing the statistical analysis. And they're important in analyzing how well your model is working, but I wouldn't get too bogged down in them for our class. And so people had a little bit confusion of the difference between measures of association and tests of significance. So these are all measures of association, and they're sort of statistical models, frames for different types of variables. And you can see how they correspond here. And so they're types, basically all you need to know about them is that they're types of tools that are used for different types of variables in statistic analysis. And they determine the strength of the relationship, but you need to use different ones based off of what type of data you have. Whereas tests of statistical significance appear in every statistical model, and they determine whether or not your findings are likely to occur by just chance, like how valid your findings are in some sense. And this is all based off of statistical theory, which I won't go too far into, but it makes assumptions about the parameters and the population. So this all deals with probability sampling if you had sampled in a probability way. And so the confidence interval, which is a part of statistical significance, is the probability that the parameter, the true value, falls within a certain range, and the degree of uncertainty within this range. So when I was talking about earlier how probability sampling allows us to measure the error, this is all within this test of statistical significance, is like whether or not if we're faced with any discrepancy between the assumed independence of variables in a population observed. So we can determine the unrepresentativeness of the sample, and we can reject assumptions of independence. And we're always speaking within probability, and you can easily remember that because this applies to probability sampling. And this allows us to measure our sampling error. Is this P is the level of significance. It's the probability of the measured associations being due to only sampling error. So this is very low, right? But we want to make sure, like, ideally we would be at 0, that there's no way that the findings we found are due to error, but we can never be perfect like that. There's always going to be some level of error, and this is what convention has defined as acceptable error. And so if we have this low significant statistical significance, if this P is this low, then it means that the findings we found were real and that there is a relationship between the variables that we developed in our model. And sometimes what researchers will do, unfortunately, is like p-hacking, where they'll like put a bunch of things into the model just to get this low, but that's a very terrible practice, because even if you get a statistical significance that is not this low, and it could mean that your findings don't have a relationship or there is error, that's a finding in itself. And your book, which I agree with, very much cautions interpreting statistical significance, because it's a guideline, like we said, it's convention, and there could also be danger. You need to take into account sample size as well. And there are also other tests, if you get more into like a statistics course, like BIC, and other tests that can compare models to determine the best one, and it might not be based off of your statistical significance. And even if your statistical significance is high, say that your results say that for every 30% increase in poverty, there is a 0.1 chance that you're going to get involved in deviant behavior. that may be statistically significant, but in practice, that 0.1 chance doesn't really make a huge deal, right? Like in practical means, that's not a large magnitude result. So you really need to think not only about statistical significance, but what does this mean practically? What do my results mean practically? And so, like, oftentimes people in causal methods will like really try to develop a relationship between two things, and they find one, but like, and it's statistically significant, but the magnitude of it is small, so it has less practical significance. So there's a difference between practical significance and statistical significance. Okay, and then chi-squared is a sort of type of test that we can do to determine, it's a bivariate analysis, so it's to determine whether or not there's a relationship between two variables. And it's like a type of statistical test. And it's different from like what I showed you earlier, the measures of association, but it's also similar. Here. In some ways, but it's bivariate in nature. And so I'm going to post on the discussion board, some people are still trying to get their discussion points, a double extra point challenge. We've been working up through this class to talk about how different research methods are beneficial or not beneficial, and their advantages and disadvantages, and what types of questions are best for specific types of research methods. So I'll post this table, and maybe people can like pick a certain area in the table that they'd like to add to, and we can sort of construct this in the discussion board as a challenge for people to review and really think about getting a bigger picture of these type of methods and what they're best for, and how their reliability and validity has strengths or weaknesses for different types of questions. And so I'm looking forward to that. Does anyone have any questions?